Multivariable calculus, drawing 3D surfaces. Here's a nice rendition by a computer of a cone. We will not expect you to be quite that fancy. Let's take a look at different views of our three-dimensional graph paper. Here's a two-dimensional graph paper as you're used to it, seeing it. And what you can do then is just bring the z-axis out towards you from the screen. Now I've drawn it on a flat surface, so it's at 45 degrees, but it's actually sticking out towards you with a 90-degree angle between it and both of the other axes. Now engineers, I'm told, like to take the YZ plane that's coming out towards you and rotate it away from you 90 degrees. And then it looks like this. And the reason engineers like this view is because it's as though they have their paper lying on the table, and their graph paper lying on the table behind them, and so they can turn around and work on it. But this isn't very convenient for mathematics because we have our positive values behind the screen, and it's difficult for us to draw that way. So this time imagine the XY plane rotating clockwise 90 degrees. And then your graph will look like this. And that's the most popular one in math books. So we like to use this. But you choose the view that is best for your particular drawing. And we also like this better in mathematics because now you have your first octant, which is the area above the first quadrant, in the front and on the right where it kind of belongs. Okay, so let's review a little bit. Here we have graph paper, the way you would normally see it, with the y-axis pointing up and the x-axis pointing to the right, and the z-axis then would come out towards you. That's one way to draw it. Now if you flip it over like this, then you have the configuration that the engineers use, with the piece of paper lying down flat on the table and the z-axis coming straight up. But the problem with this configuration is, if we have it like this, then the first quadrant is back here. Because remember, on the graph paper, this is the first quadrant, second quadrant, third quadrant, fourth quadrant. And so our first octant in 3D would be here. And then the second octant would be here and so forth. Well, that's not convenient to have the first octant in the back, in the rear here. So what we do in math classes is we turn this 90 degrees. And so now you have the x-axis coming out towards you, the y-axis going to the right, and the z-axis going straight up and down. And now your first octant is right here in the front on the right where it ought to be. And then the second octant is back here, third octant, fourth octant, and then your fifth octant then is underneath the first octant. And then you have your sixth octant back here on the right, seventh octant, and eighth octant in the front on the left. And so that's just a better, more mathematical way to do it. However, when you're drawing your pictures, you can use any configuration you want, whatever works best with your particular drawing. So if you want to do it this way, you may. If you want to do it this way, you may do it that way. Whatever's more convenient for you for that particular problem, and whichever way you like. But I will probably do it this way most of the time because that's what I'm used to. So now let's look at some simple drawings. Here we have my favorite view of 3 space, and we're going to graph this equation. Now, if this was 2-dimensional, it would be a line, right? So what's the 3-dimensional equivalent of a line? Did you say plane? Yes, this is a plane. And what we usually do is just draw a triangular portion of the plane so we can see it in perspective. So for example, if y and z are 0, then the point would be on the x-axis and x would equal 6. So I counted out 6 diagonal blocks along the x-axis. Now we need to make the tick marks bigger on the z and y-axis than we do on the axis poking out towards you in order to get some kind of a decent perspective. And so I'm going to use 2 squares for 1 unit. So when z and x are 0, y will be 3. So I'm going to go 3 units or 6 squares along the positive y-axis. And then when y and x are 0, then the point on the z-axis will be 2, because 6z has to equal 12. And so that's 4 squares up the z-axis. And then what you do is you connect those dots with straight lines, and you can see the triangular portion of this plane. Then if you want to get fancy, you can color it in and dot the axes that are behind it so that it looks like you're looking through like a translucent glass. Okay, let's try another one. X minus 2y plus 2z equals 8. This time when y and z are 0, x equals 8. So we come out 8 units. And then when x and z are 0, y will be negative 4. And again, I'm going to use 2 blocks per unit. So we'll count 8 blocks in the negative direction on the y-axis. And finally, when x and y are 0, z will be 4. And again, that's 8 blocks up the z-axis. Connect the dots. And there's a triangular portion of that plane. Now let's try this same plane, but this time we're going to use the engineering view. So this time the y-axis is poking out behind the screen. Z-axis is still straight up and down, but the one pointing to the right is the x-axis. So again, we have x equal 8, and I'm using 1 unit, 1 block per unit, because if I use 2 blocks, I'd be off the grid. And so then when x and z are 0, y will be negative 4, but we're coming out, the negative is coming out towards you, and I have to use smaller units, so each block is 2 units, so negative 4 is going to be right there. And then finally, when x and y are 0, z is going to be 4, and so I go up the z-axis 4 blocks, and then connect with lines, and then if you like, color it in to make a translucent triangular portion of the plane. So this particular plane maybe looks a little bit better using the engineering view of 3 space. All right, back to my favorite view, and this time we're going to graph this equation. Now if the z squared wasn't there, what would you have? Did you say circle? All right, well what's the 3D equivalent of a circle? Did you say sphere? Right, so when y and z are 0, x is plus or minus 5. When x and z are 0, y is plus or minus 5, and I'm going out 10 blocks because again I'm going to make the scale bigger on the y and z axis. And then when x and y are 0, z is plus or minus 5. Now do you see a sphere? It's a little tricky. So what you're going to do is you're going to connect each set of dots with a circle in perspective. So let me do that again. We've got a circle lying down on the xy plane. We've got a circle flat on that we're looking at on the yz plane. And then we've got a circle coming out towards us on the zx plane. And then if you want to get fancy, you can make the parts that are sticking out darker and dot the parts of the circles that you can't see that are behind the screen, and dot the axes that are hidden. And then if you like, you can even shade it in a nice color. There we have a beautiful sphere. Okay, let's change it up a little bit. What's this going to do? Well, this is going to cause us to have an ellipsoid. So it's like a sphere that's been stretched out a little bit. So for example, when y and z are 0, x is going to be plus or minus 3. And when z is 0, y is going to be plus or minus 3. And again, I'm making the tick marks twice as big there. But then when x and y are 0, z is going to be plus or minus 5. So I went 10 blocks up and 10 blocks down. And it's the same idea. We're going to connect these dots with circular curves. And again, I dotted what you can't see, and I made the part sticking out towards you a little darker to aid the perspective, and dotted the axes that are hidden inside the ellipsoid, and then you can color it in if you like. Now let's plot and visualize a single point in space, which is actually kind of tricky. So here's my favorite view of 3 space again, and we're going to plot the point 5, 8, 10. So we're going to start at the origin and move along the x-axis 5 units. And I'm going to use a block per unit on all the axes just for the sake of counting. So as you'll see, the perspective is going to be a little bit off, but That's why I'm going to do it right now. So we've moved 5 units along the x-axis diagonally. Now we're going to move 8 units parallel to the y-axis because we're already out in front. So we're going to move 8 units to the right. Okay? So we're not lined up straight up and down with 8 on the y-axis. We're lined up diagonally from 8 on the y-axis. We've moved 8 units from where we were. And then finally, we're going to move up 10 units straight up. And again, I'm just using 1 block per unit for the sake of counting. And so we're not lined up, to the right of 10 on the z-axis, but we are lined up in perspective. Now, you can't really see where that point is. So one thing you can do is add lines as you travel. And now you can kind of see that it's floating around there in the first octant. And another thing to help with the perspective, if you just have one point, is to create a rectangle and then another rectangle back on the z plane that's the same size, and then connect with diagonals. Now you see, because I used the same number of blocks on each axis, the 5 coming out towards you looks a lot bigger than it should. Okay, so now we're going to talk about using traces. Traces are slices of the surface on planes. And basically what we're going to do here is we're going to fix one of the variables. We're going to pick a number for one of the variables and then see what's left. What's left will be a curve in 2 variables. And we have to, of course, draw it at the appropriate place. So we're going to attempt to draw z squared equals x squared plus y squared. And if x and y are 0, then so is z, so we get a point at the origin. And then what if z is 2? Well, then we get a circle with radius 2 parallel to the xy plane, but drawn at z equal 2, so something like this. And then if z is 4, we get another circle, a bigger circle, drawn up there at z equal 4. And then if z is 6, we get a bigger circle with radius 6, drawn up at z equals 6. So we're beginning to see what this shape looks like. Now what if x is 0? Then we're going to be drawing a trace on the yz plane. If x is 0, we get z squared equals y squared, or z equal plus or minus y, which are 2 lines. And then we can shade that in, and of course z could be negative as well, so we have a similar shape down below the xy plane. So something like that. Okay, let's try another one. Z equal x squared plus y squared. This time, z is not squared. So what difference does that make? Well, again, if x and y are 0, z is 0, so we get a point on the origin. Now, what if x is 0? Then what shape do we get on the yz? What trace do we get on the yz plane this time? Well, if x is 0, we get z equal y squared, which is a parabola. So I'm plotting 1, 1, negative 1, 1, 2, 4, negative 2, 4, using 2 blocks per unit, and then drawing a parabola. Now how about we fix z at 4? Again, we get a circle of radius 2 up there at z equal 4 this time, not at z equal 2, but at z equal 4, so we get this circle right there. And so I think you can kind of see how this is shaped. You're going to get circles all the way down when you fix z values. And so what we have here is a paraboloid, and this time z can't be negative, so that's it. That's all you get. All right, now what about this one? Since we want to graph y equal 2 plus 2 sine x, this means that z could be any value. So what I want to do is make my x and y axis straight on. And so this time I'm going to have the z-axis poking out. That way I can draw y equal 2 plus 2 sine x flat on a grid like I'm used to. And that's what it looks like. Now, what do? Well, we slide each point 6 units parallel to the z-axis and draw a couple more. Actually, I drew one 3 units, slid it 3 units, and I also slid it 6 units so that I can have several things to guide my drawing. And then what I did was I connected parts of the main parts, the tops of the waves and the middle of the waves with a straight line, again parallel to the z-axis. And then to get fancy, I colored it in and got rid of what was behind this wavy, corrugated looking shape. This is actually called a cylinder, believe it or not. It's not a closed cylinder, and it's certainly not a circular cylinder, but it is called a cylinder. Okay, now just for fun, I drew it by hand using my favorite view. This time you have to draw 2 plus 2 sine x as though it were flat on the xy plane. And to help me, I actually put points on the x-axis and then 4 units above the x-axis, or rather to the right of the x-axis for the tops of the waves, and exactly 2 units to the right of the x-axis for the middle of the waves, if you can see what I did there. And then the next thing I did was directly 6 units above each of those dots, I put another dot and connected them with the same wavy line. And then again, use straight lines to connect those dots, but I dotted the parts of those lines that couldn't be seen. And then finally, I shaded it in and dotted everything that couldn't be seen through the wavy cylinder. So there's what it looks like drawn the way you would draw it on my favorite view. Okay, so now it's your turn to attempt some drawings. This will be a good skill to have when you try to set up integrals in the future, because you'll kind of have an idea of what it looks like if you sketch these surfaces first.